Hello, welcome to Functional Bar. My name is Charles, and in today's video, we'll be discussing the fold function as it applies to lists. First, we're going to talk about what the fold function does. Then we're going to talk about how there's actually primarily two different kinds of fold functions in Haskell and in other languages that provide them. We're really only going to be focusing on one of them, but we're still going to talk about that others exist. We'll worry about the foldl function signatures. Foldl is the one we're going to worry about. We'll talk about how it works. Then we'll talk about some suggestions for practice, have a quick review, and be done. So let's get started with what fold does to a list. Now, I say to a list specifically because fold can work on things other than lists. Like in Haskell, most of our major functions that everyone knows all the time can work on more than one data type, and fold works on more than lists. It's not as broad and general as map. Map works on a whole bunch of stuff. Fold works on things that are called foldable, and we'll see that a little bit later in the function signature. But we're really only focusing on lists because we haven't talked about any of the other stuff yet. We're really worried about lists, and list-like things are what fold really works on primarily. That's where we're mostly going to be using it. So what it does is it's often called reduce in more modern systems. Now reduce because fold applies a reductive operation, and here by reductive we mean, remember way back in algebra class when you had x equals 3 plus 5, we would reduce that, would see how much we could reduce it. We'd just say would add 3 and 5 and get 8, and would say x equals 8. And so that's a reductive operation. It takes something that's big and makes it small, at least when we write it out on paper. There's other types of reductive operations, of course, but this is sort of the one that I think makes the most sense and what generally is used for something like fold, what fold is generally explained in terms of, and certainly when it's called reduce. Now, those of you with programming experience, you've probably had a language that has a function called reduce. It might be on a sequence or a list or something, or an array. And you've probably heard about something called map reduce. Remember in our last video about maps and how the map function applies to lists, we talked about how lots of data processing, especially when it's spread across multiple machines, they talk about map reduce because we can farm stuff out to those different machines using map and reduce or map and fold. Now fold doesn't have to reduce. Or fold functions in Haskell and in other languages that have fold, you don't have to reduce. You could actually expand, but you generally reduce or we change something. So what I happen to prefer is to say it changes a list into something else. Now it could be a list that's shorter, it could be a list that's longer, but probably it's something completely different. When we have a list and we want to change every element in the list, remember we use map for that. The map always gives us a list of the exact same size we start with. It doesn't change the structure. A list of 10 is still a list of 10 elements after we're done with map. So fold, we could potentially change it, but there's other functions we would normally use for changing the length of a list somehow, like the filter function, which I'm just going to mention and we're going to skip right over. Another thing that fold does, that what I use it mostly for, is changing a list into a more convenient data structure for later processing. Just an example here, and I know we haven't talked about all these different data types yet, but I might take a list of book info and turn it into a map of author to book info. That is to say, I have a list of books and a list of information about books, a card catalog. I want to index it by author. I want to take an author and get all the books out of it. So I might change that list into a data structure that lets me look things up by author. And I'd probably use the fold function to do that. Now, of course, I know on a real production system would be worried about the database, but just as an example of what I do with fold and what I might be doing with fold is to change a list into a more convenient data structure. I think that's very fitting. Often, and this is that reductive operation thing again, but often it will consume a list and produce a single value. So it can consume a list of numbers and produce a single number. That's often what it's used for, is often how it's taught. I find that I seldom have to do such a simple operation with fold. There's usually other functions that already are doing that for me. And I did mention there's two kinds of fold. We're really going to be worried in Haskell. We're really going to be worried about fold L. That's left associative fold. And if you don't know what associative means, that's fine. just use foldl. It means it works, it evaluates from left to right. The other fold is foldr. That's right associative. It conceptually evaluates right to left. So it puts the parentheses all the way to the right. So it evaluates the end first and then sort of like adds on stuff to the beginning. The reason we have two fold functions is because right associative operations exist. It is completely possible that you write a function that is right associative, so to speak. And so when you do that, you might find foldr more convenient. Also, foldl traditionally has had some performance issues. Now, anytime I talk about performance, I'm also going to say never pre-optimize. There's no point to it. If you're worried about performance, you have to start with this program needs to execute this fast. And then you also need to know how to profile and find out where your program's going slow, or you're never going to make progress. We're definitely not talking about profiling, but I'm going to say if you've got a program that uses foldl and you find out that it's not going quite fast enough for you, you can try writing foldl single tick, and that does something. Haskell by default is something called a lazy evaluation, uses lazy evaluation. So the performance penalty in foldl comes from accumulating everything in something called a big func. So when we evaluate it, we sort of like build up a whole list of computations in memory and then collapse them finally at the end. And in small programs, not a problem. Any program we're writing as part of this intro course, not a problem. Production programs, probably not a problem. If it turns into a problem, you can turn it to strict evaluation with this single tick, see if it has any impact, see if it fixes it for you. If it doesn't, then you need to definitely go ahead and use your performance tools. You need to profile it to find out where the problem is, where the performance issue is. It may not be in your foldl call. It may be somewhere completely different. And usually it's your whole algorithm that needs work, not your call to foldl or foldr that needs work. It's usually not so simple. So foldl, again, is left associative. It's like math operations. I find it to be much more intuitive and easy to talk about and easy to use. It's what I generally use in my day-to-day life. I've never run into a real performance issue using it because I'm probably not, if your data is large enough, you have a performance issue, you're probably not using fold to begin with. You're going to be using something else. Foldr is right associative. If you have a function that is right associative, you may prefer using foldr. You may prefer using it for any other of a number of reasons. It may be more performant than foldl, but really you shouldn't make choices based on performance up front when you're initially writing a program. But I do need to point that out, that there are two of them, because as soon as you look in the docs, you're going to see two of them and be like, what's going on? You're actually going to see more than two of them. We'll look in a minute. So let's look at the function signature. And this is for foldl. And here in just a minute, I'm going to show you how to look up these signatures. So we've got foldl here. And you see there's a normal type specification line. This is the one in Hackage, which I'm going to introduce to you in here in just a minute. So it has foldable T. This is the first time we've seen the fat and a fat arrow, like the equal sign pointy, often called a fat arrow. Foldable T. That just means T is of type foldable, and it's T because foldable is related to traversable, and we're not going to talk about it. This just means that everything T has to be foldable. A list is foldable. We're only worried about lists, and we're definitely not worried about type classes right now. So I've written a different version of this. See, the TA says A has to be foldable. List is a foldable. So I just changed that to list A and got rid of the foldable because we're only worried about lists. So foldl, we're just going to talk about this one. It has a function as its first argument. The function takes the function as its argument. Foldfun takes two arguments and returns a result. And those two arguments are the type B. The type B here is our accumulator type. The type A is our element type. After the function, it takes B as an initial accumulator value. So it's still the accumulator type. It also takes finally as its final argument a list of type A, right? Our element type. Our element type of the list is type A, so list of type A. So where did I get this from? Because I'm going to say if you want to play with foldr, you should go look into foldr on the Hackage documentation. For good practice, and it'd be good for everyone to do that. So I'm just going to DuckDuckGo here, And this will work with pretty much any search engine, right? Google, Bing, whatever. Hackage. This is the best way to get that documentation. We type hackage space foldl. Now all of a sudden we have other stuff, right? Composable, streaming, and efficient left folds. We don't need streaming. We're worried about lists, so we're going to look at data.list. And so this is everything for lists. Now this often is going to be the case where you see a bunch of other weird stuff. So if you're worried about lists, you're going to want to work in data.list. Most of the stuff we're doing in this course is going to be data.something. So with lists, it's definitely data.list that we're looking in. As strings, as you'll recall, are lists. So everything you can do to a list, you can do to a string. So data.list is a really good place to look here. And then of course, I'm just going to search. I should probably point out there's, if I can get the synopsis open here, it gives us a list of functions and it gives us a list of their types, right? Head, has call stack. You don't need to worry about it. It's something that the compiler really worries about. If you hover over it, you see it has something to do with GHC. It takes a list of A, returns A. We have ++, which we're going to look at a little bit later in our programming examples. Takes a list, takes two lists and returns a single list. It's concatenation. So you can look here and you see there's a bunch of different folds all around here, right? There's foldl, foldl-tick, foldl1, etc., foldr. So we're going to look at foldl. This is what I got my first function type specification from, is this page, exactly this page. The reason I got it from this page is I wanted to make sure I gave you the exact right information for the function, and then I turned it into the easier read version. So this tells you what it does, and then you see here it's got some equal signs. It would be excellent practice if you sat down and you worried through everything here. So foldl, f is the function. I'm just going to give you some tips here. F is the function, and because they don't necessarily tell us that. F is a function. It's usually a function. Sometimes it's a functor. F and G are almost always used for function, the short forms of function. Z, Z stands for, I believe the mnemonic is 0, the initial value. Now remember, fold is often used in sums where 0 is the additive identity. I'm not going to make an excuse for this. I personally find Z here to be not terribly helpful, but it is the initial accumulator value. And then we have a list of a bunch of things. And then it shows us how it is applied, or what it equals. If we were going to expand that with our parens, remember the parens are the order of operations. So the ... means it can go on to infinity, which is, yes, Haskell can do that. It'll never end because it's infinite, but it can go on. And it says that we start with z, f, x1. So let's say z, the initial value, f, let's say that's plus, x1, let's say 1. And we're going to do something very similar. And then it takes that result, which evaluates to 1. Then f, we're going to pretend is plus, x2 is, let's say it's 2. So it's 1 plus 2, and then we keep going until we get to n. So if you worry about this, even if you spend 20 minutes on it and still don't understand, it's fine. The exercise is helping you. I promise the exercise is worthwhile, even if you just feel frustrated at the end. Go to sleep, come at it tomorrow, whatever. Fold R, the other major version of fold, is right associative. So one of the things you might do, you see it's got a similar type signature. Let's start at that first. Remember, lists are foldable, so this TA here is just list of A for our purposes. And you see that the function it takes, the fold fun it takes, is different. It takes an element first and an accumulator second, which is the reverse of foldl, which takes the accumulator first and the element second. And then, of course, they both return the accumulator. The initial value of the accumulator, the traversable or the foldable A, which is a list, and then it returns B, the accumulator value. And we have a similar thing here that we had before in the fold function, foldl function. And we see that the parens are different. We have x1, let's just pretend this is 1, 2, 3 again. So it's like 1 plus, and then we do some other stuff here, 2 plus some other stuff. And then finally, what we're actually going to wind up doing is saying, let's say n is 10, 10 plus our initial value is 0, and then that gives us is 10, and then we'll add 2 to it, and then we'll add 1 to it, whatever. So it comes like it's just where these parents are is a difference. So here in fold R, we start at the far right. We start evaluating at the far right, and then we keep evaluating to the left. Sort of conceptually, we're moving to the left, from right to left. We're conceptually moving from right to left. So it feels backwards. Fold L, however, we are moving from left to right. And then you notice here's the fold L tick. With strict application of the operator, the only reason you do strict is for performance reasons, really. So if we talked about that already. So to get to your documentation, to find these function signatures, you search for Hackage, and then the function you want, or the module you want, data.list, is what we're in. One of the nice things about Hackage, just to point it out, this is, again, don't worry about the implementation. People who write these library implementations do so with a lot of things in mind. And if you're a library maintainer, you very well may care a lot about performance. There's a lot of people who work on this. We see that it has app endo, get dual, fold map, dual, endo, flip, blah, blah, blah. So we really don't want to be worried about that. This is stuff we don't know yet. So we're going to ignore that. We're going to focus on what foldl does so that we can use it, because we don't have to understand the implementation to use it. And in fact, the list implementation in Haskell is probably something very different from any other programming language, any non-functional programming language, but we don't care. It acts like a list. So we care about how it behaves. We don't care about the implementation details. And that's a very common thing in programming. So don't get tied up in that. The reason we have these abstractions and these functions is so we don't always have to know all the complicated stuff to make everything really awesome under the hood. We can use the work that people have done before us that's awesome to build our own awesomeness on top of it. Standing on the shoulders of giants is what people often call that. All right, so that's enough of that. We talked about the signature. We care about the fact that it takes a fold fun as the first argument, takes an initial accumulator value, takes a list that we're going to fold across. So how does this work? And now we're going to go to our program. You see I've already got some stuff here from when I was practicing for the videos, so I'm just going to real quick change this back. All right, so I'm going to run it, make sure it works. No errors, no warnings. We got 6, which is what I expect, because our fold fun here, and you normally not write, this is for teaching purposes. This is didactic. It's educational. We would, in production code, never call this fold fun. We might call the parameter fold fun, but we would never call the actual function we're passing in fold fun, because it's not meaningful. We would write add. Would use add, and in fact, would probably use for this one. It is exactly the same thing as plus, because remember we can write plus this way and it turns into a normal function. So we could pass this in. But for now, I think that confuses the issue. The issue that we're focused on now is foldl. We're not worried about how to write the most elegant Haskell code or the most meaningful Haskell code. I just wanted to point out that what we're doing here is very didactic. It's very education oriented to try to make it easier for you to understand. It's not what you'd write in production systems. So we have our normal main program here. We have a list called L. And just as 1, 2, 3, it's a list of ints. And now we've got R, a result, which calls that foldl function. We'll talk about that here in just a minute. And then finally, we put Sirlin, show R. This should look very similar. We've done very familiar to. We've done similar programs before to sort of step through our work to show how things are being done. So we're going to keep up with this pattern here. Now let's look at foldl. Foldl you could write in one line, and probably for something like this you would. I happen to prefer this form if anything's particularly large, especially if I've got a lambda here instead of a function. And in this example, I've written things out so we can look at those arguments. so we can see what's going on. So fold fun here is our fold function. The function we'll be applying. It's a binary function. Remember, this is the same thing we saw in our type signature just a minute ago for foldl. The first thing it takes is a function, a binary function. And that binary function takes an accumulator type, an element type, and returns an accumulator type. Now here we've got a list of ints. And we didn't have to say list of int because we could infer it because we're calling fold fun with int. And our fold fun here takes an int as the accumulator value and an int as the element value. Now I do need to point out accumulator and element may be different. It says B and A. It doesn't say they have to be different. It says they may be different. They can be different. It's completely possible they are the same type. Inside the function implementation, they work as different types, but outside we can pass it the same type and it's fine. So we have our accumulator value. There's a parameter for the accumulator value in fold fun, and we have our element value, which gets passed in for this parameter. And then we're just adding them. So fold fun right now just adds two things together. So it is exactly the same thing as just the plus sign, but I'm writing it out this way to make things a little bit easier to reason about, I feel. At least to me, when I was studying it the very first time, this is how I did it all the time. And so I hope that you don't go through the same pain I did when I was fighting with the weird plus sign all by itself. So I'm just going to write it this way. And so it just sums up. It sums the list, right? 1, 2, 3, 3, 4, 5, 6. So here's another difference between left associative and right associative. Left associative would say 1 plus 2 plus 3, 1, 2, 3, 4, 5, 6. Right associative would do 3, 4, 5, 6. And of course, for addition, it doesn't make any difference. So I'll just, oops, not on the right window. And it is 6, so we can see that works out just the way we think it works. So let's step through that a little bit to see what's going on. So we have foldl, and we're not going to dive into foldl as through its implementation. We're going to focus on what foldl does, not how it does it. So foldl, it takes fold fun as the first argument, 0 is the initial value, L for the list. I'm going to go ahead, and that's just what we have down here. I just wrote it out all in one line. I'm going to go ahead and write out the actual list here so that we can see it right up here while we're working through things. So what foldl does, it says, okay, I know what my fold function is. I know how to, I know that operation. I can do that operation. I know my initial accumulator value is 0. So I know the very first thing I'm going to do, I'm going to go ahead and note down my accumulator is 0 now. And then we have a list of 1, 2, 3. So I have a first element of the list, and that first element of the list is 1. So what foldl is going to do is call fold fun with the initial accumulator value. This is the initial time it's been called, plus the element, or with the element as the second argument, which is 1. A fold fun, remember, just adds right now. So 0 plus 1 is 1. I've got another element in the list, right? It's 2. So we can keep going. So it calls fold fun, but now it uses the result of the previous invocation. So this 1 here is now the accumulator value. So it's 1. The element is 2. Remember, we're on the second element, so it's 2. So we add those together. Remember, it's just fold fun is just accumulator plus element. So it's 3. We have another element in the list. The final one is 3. Our accumulator now happens to be 3 as well. So we've got the accumulator of 3, result of the previous invocation, and then we've got the last element, which happens to also be 3. We add those together and we get 6. Now foldl is looking at this and says, oh, there's nothing else to do. The way this works is I can't do any more. So my answer, my return is 6. Just the final return of the final fold fun invocation, which would be the next accumulator value, is just the return from foldl, or any fold function for that matter. So that is equal to 6, and that's how we get there, right? So we just sort of like call this with our accumulator, right? 1 is from here. This 0 is from here, the initial accumulator value. This 1 is from the previous invocation. This 3 is from the previous invocation. This 6 is the final accumulator value, and that's what gets returned. Now, let's look at what happens if we were to change our accumulator value. So I'm going to leave this here so you can see it. I'm going to write more. Let's change that to 3. All it's going to do is, because we're adding, all it's going to do is continue to, is going to get the result plus 3 or something. So we'd go through this again. So we say foldl looks, says I have a fold fun. I have an initial accumulator value, which is 3. I'm going to change it. I'm going to make this a little more specific, which is 3. And I have a list. So I can start adding, I can start folding across this list. So the first element is 1. So I'm going to call fold fun with my initial accumulator value, which is 3 now, remember, because our invocation here starts with 3. Our initial value is 3 for the accumulator. And the first element of the list is 1. And fold fun is just add, so we're just going to add those together, so that's 4. We've got another element of the list, which is 2. So we call fold fun with the previous function, the result of the previous function invocation, which is our new accumulator value of 4. And then the second element of the list, which is 2, which is, so we add those together. That's all fold fun does right now. So it's 6. And then we can fold again. We've got a 3 here, right? Our final element. So the result of the previous invocation is 6. And then we have our final element 3. So that results in 9. So now there's no more. There's nothing more to fold across. So the result is going to be 9. So that one up here is going to be 9. So all it did is change our value. So it did the same thing. It's just instead of using 0, which is nice for adding because it's an additive identity, it's 3. So we started adding at 3, 3 plus 1, etc. And we look down here, the end result is just exactly what we added, 3 to everything. Nope, 3 plus 3 is 6. Plus 3 is 9. So we've got exactly what we expect there. So let's look at one other case. It's kind of interesting. If we had the empty list, there's nothing for foldl to fold across. So foldl just returns the initial accumulator value, right? There's nothing to call fold fun on. The result in this case, and this one right here, is just going to be 3. So the empty list is always, it's perfectly valid to pass in the empty list, but the result is going to be the initial accumulator value, which is what we'd expect. But we needed to call that out specifically so we know for sure. Now let's change this to a slightly different function. This time we're going to fold across a list of strings, and we're going to sum up the length of the lists of strings. We use an apple a day. So we have some different numbers in there. Now our fold fun here isn't going to work anymore, right? Because we have a list of strings, not an integer. So this, remember, from our definition, the fold function takes an accumulator value and a list element value. This list is a list of strings. So the elements are strings. So we have to pass a string. We have to change this to a string. Now we can't just add a string to an integer. That's not a thing. In some languages that would be append, and it would maybe do some type promotion. Haskell doesn't do any of that. We just cannot add an integer and a string. There's no way that makes sense anywhere. Instead, we're going to take the length of that string. Right? So we take our accumulator, which is an int, and we're going to add it to the length of the string. And so we're going to wind up counting all the characters and all the strings in this list, which for strings is probably not something we particularly care about, but it may be if we wanted to find the number of characters in a file, right? Like if we read a file, it tends to come across as a list of strings with each line being a string. And so we could do this to count the number of characters in a file. So there are some use cases for this sort of thing. It doesn't come up too much. Again, this is so we can help ourselves to understand this. So we have a string, we have a list of strings. You'll notice we didn't have to change anything down here. Our accumulator value is still 0, right? Because we're summing the number of characters in all the strings in this list, in the list L, and we have L. And that's part of that is why the fold function is so powerful. Fold functions, I should say, because remember there's more than one. They're so powerful because we can do these very different things just by changing the function we pass in. So let's see what happens here. I'm going to write this out again. Actually, let's run this. Let's make sure it does what we think it does. So let's count our characters. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We expect it to be 11. So let's run it. And it is indeed 11, just like we expected. So let's work through this a little bit. We have foldl, fold fun, 0. And I'm going to copy paste this list for us because we don't want to wait for me to copy type it. All right, so foldl comes in. And first thing he does, he says, I know what my fold fun is. I know what my initial accumulator value is. And here's my list, and it's not empty, so I've got stuff to do. I have a first element, so let's go ahead and get started. We're going to call fold fun with the initial accumulator value, so 0, right? The initial value, it's a first invocation for the first element of the list. The initial value is 0. So that's our accumulator value. And then the first element of the list is an. Excuse me. And so we look at fold fun, it's just a length of element. So I'm not going to expand all of this again for us. I think we can all look at this and say, okay, an is 2. And our accumulator is 0. So 2 plus 0 is 2. Or an is not 2. An has 2 characters. So the result of that is 2. Now foldl comes back and says, okay, I've got another element of the list. It's apple. So I'll call fold fun again. Now our accumulator, the result of the previous invocation is 2. And the element is apple. So apple is 1, 2, 3, 4, 5 characters. 7. 5 plus 2 is 7. We have another element of the list. We just finished with apple. So now we have A. Now the accumulator value, we're going to call fold fun. The accumulator value is the result of the previous invocation. So it's 7 now. The element, as we just said, is A. A has a length of 1, so it's 8. So 7 plus 1 is 8. We have another element of the list. It's day. Our accumulator is 8 now. The previous indication is 8, so the accumulator value is now 8. The string day is the last element. Day is 3 characters long, so 8 plus 3 is 11, which is exactly what we would expect. And in fact, it's what we got previously, so we're doing well. We figured it out because there's no more elements in the list. The final fold fun invocation, the result of that, the final one, is the return of foldl. So we folded across a list of strings and used the fold function to count the number of characters in all the strings in that list. So that's it for our walkthrough of how this works. So let's talk about some suggestions for practice. I am aware that probably after you've read that, after we've been through that, some of you are like, I still don't understand fold. That's okay. What you should do is work on these practice exercises. Write some programs that use foldl. If you're having difficulty, stick only with foldl. Don't do anything else. Only stick with foldl and write some things using foldl and write out what you expect it to be and how to get the answer. And then go back and maybe rewatch just that section of the video so you can watch how I'm walking through it, and maybe try to, on your own, write out what you expect to happen with those invocations like I did. That'd be good practice also. But sometimes it just takes a while to learn these functions. You just have to work with them a little bit. So some suggestions for practice, and again, you can come up with any number of exercises you want. And one of the great things about programming, software engineering in general is we can find a problem, we can give ourselves a problem and find the answer by hand, make it simple enough you can find it by hand, and then go write the program to do it. And then we can make sure that we've learned how to program for that problem. So the first thing is to compute the product of all the elements in a list of ints. Now we already did that for computing the sum. This time it's compute the product. And really remember the initial accumulator value here. 0 is the additive identity. So when we're adding everything in the list, we use the additive identity. For product, we want to use the multiplicative identity, which is 1. So our initial accumulator value should be 1 when we're multiplying everything together. And so you can write this out and you can change that 1 to a 0 and see what happens just for fun. And then remember some basic math and why you thought you'd, at least when I was going through that class, I'm like, when would I ever use this? And it turns out I use it fairly regularly for the identities, the multiplicative and additive identities. The next exercise is concatenate a list of strings into a single string. It's very similar to what we just did. Not quite, it's just very similar because we're working on strings. What we're going to do is we're going to take a list, like an apple a day, so a list of strings, and we're going to smush all those strings together into one string. So you can write this as returning a list of strings. You could also, into a single string. I had my example wrong there. You could have it return a list of a single string, but just return a single string is what the problem says to do. So we have the list an apple a day. We just turn it into an apple a day, no spaces. Right? We do not use spaces here. Now I need to point out this is a commonly used function called concat that works on all lists. Don't use that function. Write the foldl function to do this for you. Don't use the concat function. If you wanted a space in production, there's a different function called intercalate that would add the spaces for your another character. We don't need to use that function here either. We're just going to smush them all together into one string and write the fold function to do that. Now, in order to do that, you're going to need to know the append operator. Now, remember this, I'm going to show you for lists, but remember strings are lists. So plus plus is the append. It takes a list, it takes two lists actually, and returns a list. And we saw that on Hackage just a minute ago. So here's two lists, 1, 2, 3, plus plus 4, 5, 6 is equal to 1, 2, 3, 4, 5, 6, one list. So this is what we need to use this append operator on our strings. Now this is a more advanced exercise. Remember, like more advanced than the previous one. This should be relatively simple once you get there, but what makes it a little more complex is when you have to start thinking of strings as lists. So remember, the plus plus is a list operator, but we use it on strings to concatenate our strings as well. So you can practice with that, and that would be an excellent exercise. Start getting used to some more string manipulation. And then the final exercise is the most advanced. Sum the square of every element in a list of ints using only foldl. So here's an example. Let's say we have, for our function, we're going to take the list of 1, 2, 3, and it's going to yield us 14. Now, why did it get to 14? So the first thing it did, it turned it into a list of squares. So we square 1 squared is 1, 2 squared is 4, 3 squared is 9, and we add these together. 9 plus 4 plus 1 is 14. So for this exercise, you should use fold function, foldl. And a real program, and I'm going to show you what we do in a real production program because I don't want you to think that this is necessarily, this is a great example of how to practice with fold. You may actually do it this way in a real program, sort of depending, but probably you would actually put two functions together. One of the really big advantages of Haskell, huge advantage of Haskell, is we have these little functions and we can just sort of glue them together and make another function. And so it's actually more maintainable and more readable that way in general. Not every specific case is going to be like that, but in general, it's going to wind up being more readable and more maintainable. And we'll be using library code, so we can expect it to be reasonably fast as well. So I've written this out in sort of a half and half way of what I would expect a seasoned Haskell programmer to write it. I'd expect them to use something a little bit different. But this, I think, is really good for demonstrating sort of halfway where it goes. So we have our square function as int, and you're going to need to know this, how to square something. You could just do x times x, but you can raise something to a power in Haskell by having the number pointy, arrow pointy up. That's the caret, shift 6 on US keyboards, 2. So that's the same thing as if you had written 2 with a 2 superscript or x with a 2 superscript in math. And you can write it this way if you like, whichever. I happen to prefer the extra space around it when we're writing it out. So you could also do something like 3 raised to 2 is 3 squared, or 6 squared. Right, you can do those and you raise that. That's just how you square things. It doesn't have to be a 2, it could be a 3, it could be an 8, just whatever power. So that just raises it to that power. I've written this as square to make it perfectly obvious that we're just squaring integers. So this function is called sum squares, and it takes L, our list, with the int, and then we just say sum, a $sign, remember that's how we do parentheses, so we're putting a parentheses on this back end. It's a shorter way to do it. It actually is apply. It says apply everything afterwards. So map square L. So remember, map turns a function that works on one thing into a function that works on lists, or applies the same function to every element in the list. Both are true, right? They're both the same thing. So we apply the function square to the list L with map. So map square L, the list. So that's going to compute this. It's going to give us a list of the squares of everything in L. And then we just add them together with sum. So we've stuck our two functions together. We can sort of compose them this way. And then we'll get the same answer without having to write fold or foldl, which often is going to be considered better. And if you're a real hardcore person, you'd probably do something closer to just because I showed you that hackage page, I want you to start learning that stuff like this happens and kind of how to read it. Partial application, because this whole thing is going to expect, right, we have an L here, but it's at the end, and that's just our name for the argument. Because of partial application, we can do this, and the whole expression is going to be evaluated. It's going to be kept, and it'll know that this turns into just a function that expects L. And in fact, you may actually use function composition with a dot operator somewhere. So we'll get to all of that later. I just kind of wanted to point it out to you. For now, remember this exercise, you're going to be using foldl. And then after you've got that done and you're comfortable with using foldl, you might try writing something closer to this, where we're using sum and map together. All right, and that's it for our suggestions. So let's go through a quick review. We talked about what fold does to a list. The biggest thing that it does to a list is it takes a list and it turns it into something else. And a sub case of that, a subset of that functionality, is it will take a list and it will reduce it to a single value. So a list of ints into a single int, or potentially a list of strings into a single int, whatever, what have you. But it takes a list and it turns into something else. We talked about how we would not use it to reduce the number of elements in a list. There's a different function for that called filter, which you can look up if you happen to need it tomorrow. We'll get to it eventually, but not right now. The focus of today is on fold as it applies to lists, especially foldl as it applies to lists. We talked about how there are two primary kinds of fold in Haskell, foldl and foldr. Foldl is the most intuitive because it's left associative. It's what we generally expect to happen. Foldr also exists. You may use it if your function happens to be right associative or your operation. Generally, we're focused on foldl for right now. You can start practicing with foldr. It'd be a good idea to practice with foldr. In general, foldl or foldl with that tick is going to be more than sufficient. We looked at the foldl function signature, which introduced a little bit of new syntax with this fat arrow here and the thing over here, the foldable T. We just glossed over that real fast. We don't need to know anything about this now because we're not at all ready to talk about what that means. But since we're starting to look at hackage, we do need to know that these things exist and sort of how to work with them. So T, foldable T, a list is a foldable. So if we see foldable T, that means it's a list. So it's a list of A. And I just wrote this down here more for clarity using the stuff that we already know, where we have our function, our accumulator, our list that we're folding across, and then the return, the result. We spent some time walking through how fold works in actual Haskell code, and then we didn't step through it with all of our expansions like we've done previously. Instead, we talked about what it does from a higher level, just looking at when the fold fun gets applied and how we get the accumulator for that and how we get the result for the whole function. We reviewed some suggestions for practice as always. We have two that it gets a little steeper in the difficulty than we normally did. We have a pretty easy one, should be something like we just did. Turn a list of strings into a single string. The difficulty here is only that you're dealing with a list of strings. Strings are lists, so it's really a list of lists. So we talked about this before, how we need to switch between string and list in our mind when it's appropriate. So that's where the difficulty here comes from. Otherwise, it should be very straightforward. And then we talked about sum the square of element in a list of ints. And we talked about how we're going to do that for foldl. We use foldl for our practice, foldr as well if we want to. And then we're maybe, as a stretch goal, this is already a stretch goal, but a stretch goal to a stretch goal would be we also write it using map and sum so that we can compose two other functions like I showed you there, just for some practice, just to get some idea, the feel for how you might see this in production Haskell code. And that's it for today's video. As always, questions and comments are welcome. Thank you for watching. Please click like and subscribe, and I hope you have a wonderful day.